Morning, everybody. Thanks for the invitation to present the risk mapping tool that Sweco has developed in collaboration with Transport Scotland. Here's a quick short overview of what we're going to present today. I'll do the first 3 slides from a client's point of view, and Panos will do the last 3 sections more on GIS, which is more tailored to the audience here today. So as an introduction, why did Transport Scotland commission a GIS-based route risk scoring tool for the trunk road network? Well, firstly and most importantly, it's one of the tools we will use to try and achieve the goals set out in Transport Scotland's Road Safety Framework to 2030. Firstly, this is for Scotland to have the best road safety performance in the world by 2030. We aim to achieve this by reducing the number of people killed or seriously injured on our roads by 50% by the year 2030. The framework also sets out an ambitious and hugely compelling long-term goal for road safety in Scotland, where no one dies or is seriously injured using our roads by 2050. Traditionally, one of the main methods of reducing road traffic casualties in the trunk road network was to investigate where collisions had occurred, particularly cluster sites, where 3 or more personal injury accidents have occurred within a 100-metre radius of each other in the most recent 3 years. Then understand the cause of these accidents and implement measures to stop them happening again. However, national statistics for road casualties reported to Police Scotland in 2019 showed that the total number of casualties had fallen to the lowest number since annual records began in 1950. This year-on-year improvement in road safety has made it much more difficult for us to identify cluster sites and to target mitigation measures to improve road safety. While we will still continue to investigate collisions, this route risk mapping tool will allow us to identify risk rather than cluster sites. It will allow us to be more proactive with regards to road safety, i.e. we're doing something before it happens. It will assist in improving our road safety performance of our infrastructure. Bear in mind, human beings are fallible and they will make mistakes. Reducing risk on the trunk road network will help us mitigate the severity of injuries should a collision occur, i.e. make the roads safer and more forgiving of errors by drivers. While these targets appear very ambitious, and they are based on Vision Zero, a concept implemented in Sweden in the 1990s and has now been adopted throughout Europe and further afield in the world. Works on the basic principle, pretty simple. It's unacceptable for anybody to be killed or seriously injured using our roads. Vision Zero follows a safe system approach, which you can see on the screen here. Basically, the principle is road safety is the responsibility of everybody. As you can see from the slide here, namely it's safe road use, that's the user, safe vehicles, that's manufacturers, safe speeds, that's users again, post-crash response, that's emergency services, and what this tool addresses, safe roads and roadsides. In a safe system, safe roads and roadsides are designed to be designed or improved to reduce risk and to mitigate the severity of injury should a collision occur. Transport Scotland's 4 operating companies have been issued with this tool this year, and they're actually using it just now to actually start looking at the sections which are demonstrating higher risk than other sections. And what we've tasked them to do this year is, for the end of the year, come forward with measures that they can maybe look to do in future years to actually reduce risk on the network. Transport Scotland will be funding from 23-24 onwards budgets to start removing this from the network. So the data we've used for actually populating this GIS tool, basically we've used the existing inventory that Transport Scotland holds. It's called IRIS. It's a database which holds all the information on everything we've got on the network. We did this rather than doing a LiDAR survey because we've got the information already. IRIS is a database which has everything that Transport Scotland owns, manages and maintains. So that's every sign, every lighting column, every gully, everything in the trunk road network's there, i.e. everything you could class as a hazard. In addition, IRIS records the road condition data, things like the geometry of the road, skid resistance, quality road markings, extent to speed limits, etc. This was all the data that we used to populate the GIS. I'll now hand over to Panos.
Hi everyone, my name is Panasiotis. I'm a principal GIS consultant at Sweco, and I was the GIS lead for this project, working closely together with Sweco's road safety team and Transport Scotland. So, let me talk a little bit about the four main challenges we faced. Sweco undertook a desktop study to review and assess route scoring systems and methodologies used in Europe, Australia, and the USA. Apart from the Republic of Ireland, who provided us with the principles of their approach, only high-level information was available for the other systems in terms of methodology and mapping. With a reducing number of accidents in Scotland, identifying cluster sites and trends from accident data alone is becoming more difficult. So, going forward, a risk mapping system that identifies risk based on road infrastructure characteristics and roadside hazards was required. Sweco considered information readily available through Transport Scotland's integrated road information system. During this process, issues that had to do with data availability, accuracy, and consistency were revealed and dealt with. Sweco developed a GIS-based route risk scoring system which incorporates a model for the calculation of the route risk scores, automation for data digestion, space analysis, and geoprocessing tasks, as well as a dashboard developed to map the risk score calculated for each section of Scotland's trunk road network and offer querying and filtering capabilities such as access to key performance indicators. In a nutshell, the solution we developed and implemented is called Route Risk Scoring Geographic Information System, an innovative GIS-based system which integrates assets and features of the Scottish trunk road network into a central geodatabase, runs bespoke multi-criteria analysis in the form of custom model tools and script tools developed with Model Builder and Python for ArcGIS to calculate the required risk score and KPIs, and maps and visualizes location-based analytics through the route risk scoring dashboard, an interactive cloud-based ArcGIS dashboard for ArcGIS Online. As part of the route risk scoring model, the existing links and sections of the Scottish trunk road network needed to be processed to create new uniform 500-meter long sections. The new sections should have the following common characteristics: carriageway type, speed limit, and length. Altogether, over 10,000 new sections were created with over 4,700 kilometers of total section length. In this figure, you can see an example of a linked section being split into 8 new sections. Having the newly created section as the backbone of our solution, we started building our route risk scoring model using 20 hazard factors based on the information collected from Transport Scotland's asset management systems and other open data sources, which were then grouped into 4 hazard scores, namely alignment, environmental, roadside, and condition hazard score. These 4 hazard scores are used to calculate the total hazard score per section. So the total hazard score is the summation of the calculated hazard scores per section, and the total risk score is the product of the total hazard score and the exposure factor per section, with the exposure factor deriving from the annual average daily traffic on a section. But not all hazard factors and scores are equally important. Using the analytical hierarchy process, we analyzed, organized, and quantified the weights of the factors and scores, with the total sum of the weights being 100. Each factor is then normalized, with its maximum value being the weight assigned during the AHP, and the theoretical maximum value of the total hazard score being 100. So, this graphic summarizes all hazard factors and scores we considered with their assigned weights and how the total hazard score and total risk score are calculated per section. Apart from the hazard factors and scores, the following 9 collision rates have been calculated per section to assist in identifying sections of high risk to target mitigation measures such as all accidents rate, fatal weighted injuries rate, and killed or seriously injured rate. Now, looking at the development of the route scoring GIS, it has been based on this architecture. Desktop GIS level. where we have ArcGIS file databases and other GIS-compatible file types for data storage, ArcGIS Desktop for data management, geoprocessing, speech analysis and mapping, and Model Builder for developing custom model tools and script tools. FME Desktop runs at this level as well, with workspaces developed for data ingestion tasks. Next, we've got the GIS web level. This is where ArcGIS Online lives, a cloud-based platform where the route scoring dashboard has been developed. And finally, we've got the end users level. Backend users, such as GIS professionals, are responsible for maintaining and updating the data, applications, and tools at the desktop level and the content on ArcGIS Online. Front-end users, such as managers and executives at Transport Scotland, and then operating companies, can access the dashboard through a web browser to interrogate information and make informed decisions. Also, users could access the online content, such as the hosted feature layers, to enrich a web map or inform a report, or use them in a web map with ArcGIS field maps or Survey into 3 on their mobile devices for a site survey or an inspection. The required data for the route scoring GIS has been stored in an ArcGIS file database and as individual raster datasets, with a data theme spanning across several categories, such as collisions, road conditions, and safety fences. The data has been used with the custom model tools and script tools to calculate the hazard scores, collision rates, and total risk score for each 500-meter long section. Geoprocessing and space analysis workflows were developed for data ingestion, calculations, overlay analysis, proximity analysis, and surface analysis, with some examples of these tasks shown on screen. Due to the large amount of data used and the number and complexity of the workflows required, automation was deemed necessary. So, Model Builder and Python for ArcGIS were used to automate the geoprocessing and space analysis workflows, resulting in developing 54 custom model tools and 12 custom script tools. Also, several custom model and script tools for Model Builder and workspaces for FME Desktop were developed to automate the required data ingestion workflows. The main output depicts the sections allocated into 5 color-coded categories of total risk score, from green, continue to monitor, to amber, considered for investigation, to black, high priority for investigation. This map document has been published as a hosted feature layer to ArcGIS Online, and based on this, 5 hosted feature layer views have been created for the route risk scoring dashboard. This map output depicts the collisions allocated into 6 color-coded categories of accident severity, from green, slight, to amber, serious, to black, fatal. This map document has also been published as a hosted feature layer, and based on this, a hosted feature layer view, collision, was created. The route scoring dashboard web map has been developed to fit the route scoring dashboard, and it contains the 6 hosted feature layer views mentioned previously as its operation layers. Now, the route scoring dashboard has been developed to map the total risk score calculated for each section of Scotland's track road network and offer querying and filtering capabilities as well as access to KPIs through a series of configurable elements such as map, list, charts, gauges, indicators, and selectors. So let's see a demo of the dashboard. At the center, we've got the map element, where we can access the layers list and the legend of the active operational layers. There we've got 2 stacked indicators displaying the number of sections and the sum of lengths of the sections, and a list displaying the summary of the section's attributes. A donut chart displaying the number of sections per speed limit, a bar chart visualizing the number of sections per total risk score scale, and a table presenting the main data attributes of the sections. At the header next to the dashboard's name, we've got 3 category selectors: road name, section type category, and operating company areas. Below that, there are 9 stacked gauges displaying the number of sections with a positive collision rate, And below them, we've got 14 stacked donut charts displaying the number of sections with score or rate within the top 10% of the values. In the side panel, there is a bar category selector for the total risk or scale and 14 number selectors displaying the total risk or hazard scores and collision rates. Now let's run a quick scenario for the sections within the high priority and priority for investigation, where the values of the killed or seriously injured rate are within the top 10% of the values. Then let's focus on the A9 route. And let's pick from the list this section. From the pop-up window, we zoom to that section, and then by scrolling down, we can view the general attributes of the section. Open the link to Google Street View in a separate tab in our browser. Have a look at that section of the road network. And then carry on viewing the risk and hazard scores, risk rates, and at the bottom of the pop-up window, the hazard scores column chart. And by clicking the right arrow, the individual charts for the hazard factors of the hazard scores: alignment, environmental, roadside, and condition. Then, using the table, we can download the CSV file with a full attribute table of the section shown on the map and in the table. Finally, the deliverables of our system included the desktop GIS data, maps, and custom tools, which were packaged into a zip file, and the WebGIS content that was cloned from Sweco's ArcGIS Online organization to Scottish Government's organization using geodatabase backup.my.org app. Also, by configuring URL parameters in the dashboard, we provided the operating companies with access to their areas of interest only. Before I close our presentation, let me present the main benefits and takeaways from the developed solution. The central geodatabase provides a single source of truth. The custom tools ensure accuracy in performing the required spatial analysis and geoprocessing tasks, while the time required to run the processes is minimized. The ArcGIS dashboard provides a dynamic, data-driven view of geographic information, offering a comprehensive view of the data and providing key insights for an at-a-glance decision-making. Transport Scotland can use the dashboard to make informed decisions about where to target funding to remove risk on the track road network. And finally, Sweco has successfully leveraged the ArcGIS technology that Transport Scotland has access to by creating an innovative, bespoke technical solution that improves the return on investment and adds value to their assets, data inventory. Thank you very much for your attention. If you have any question or wish to reach out to us, please speak to Robert or myself at one of the breaks, or email us at the email accounts shown on screen. Thanks again, and hope you enjoy the rest of the conference.